All right, let's get right into it. Deep inside every single piece of modern tech, your phone, your computer, you name it, there's this incredible microscopic dance going on all the time. It's this wild battle of forces, a migration of charges, all happening on a stage so tiny it's almost impossible to picture. So today, we're going to pull back that curtain and really get to know the absolute foundation of all electronics, the p-n junction. You know, if you look at any of the big players, diodes, which are like one-way streets for electricity, transistors, the little switches that make all computing possible, even LEDs that light up our world, well, at the very heart of every single one of them, you find this one thing, the p-n junction. It's the fundamental control valve. So before we can even begin to understand how our devices do what they do, we first have to understand this junction in its natural resting state. So that begs the most obvious question, right? How do you even build something so precise? I mean, we are talking about a perfect connection, right down to the atomic level. How in the world is that done? Now, your first thought might be, well, just take a block of one type of material and a block of another and squish them together, right? But nope, that absolutely will not work. And this slide shows you exactly why. At the atomic scale, the distance between atoms is just unbelievably small. We're talking 2 to 3 angstroms. For perspective, a single human hair is about 500,000 angstroms wide. So any surface, no matter how perfectly polished it seems to us, looks like a jagged mountain range at that level. That physical gap makes any flow of charge pretty much impossible. The real way is so much cooler. You actually start with one single, perfectly continuous crystal of pure silicon. And then, using a process called doping, you introduce these tiny, targeted impurities into different parts of it to change their electrical properties. This is how you get 2 totally distinct regions, a p-type and an n-type, all within one single unbroken crystal. That's the secret sauce. It's not 2 pieces stuck together, it's one piece with 2 different personalities. So let's meet these 2 personalities. We really need to get to know the 2 populations of charges that are the main characters in this entire story. Okay, so on one side you've got n-type silicon. The N stands for negative. It's been doped so it has this huge surplus of free-moving electrons. They're the majority around here. Then on the other side you've got p-type silicon, P for positive. This side is doped to have tons of what we call holes, basically spots where an electron should be, and they act just like a positive charge. Here, the holes are the majority. It's this massive imbalance that sets the whole stage for everything that's about to happen. So what do you think happens the very second we create this junction? You've got this huge crowd of electrons on one side and this wide open space full of holes on the other. And if there's one thing nature can't stand, it's an imbalance like that. And this is exactly what happens. A huge migration kicks off, and it's driven by nothing more than this difference in concentration. It's kind of like opening a door between a totally packed room and an empty one. The electrons from the crowded N side just rush over to the P side to fill in all those available holes. At the same time, the holes from the P side effectively move over to the N side. This massive movement of charge, well, that's what we call the diffusion current. But here's the plot twist. This whole chaotic rush to find balance, it has a really important and kind of unexpected side effect. As all these charges move across the border, they leave something behind. Okay, this is a super important detail. To start, both materials are totally neutral electrically speaking. For every free electron in the n-type material, there's a matching positive ion, the atom it came from. So when a free electron wanders off, it uncovers that positive ion. And here's the key. That ion is locked into the crystal structure. It can't move. The exact same thing happens on the p side. A hole gets filled, uncovering a fixed negative ion. So right there at the border, you get this amazing new zone. As the electrons and holes cross over, they basically cancel each other out, leaving behind this wall of fixed positive ions on the n side and a wall of fixed negative ions on the p side. This area, which is only about 1/10 of a micrometer thick, I mean, it's so thin you'd have to stack about 100 of them just to match a single sheet of paper. This is called the depletion region. Why? Because it's been totally depleted of any free mobile charges. And what happens anytime you get a separation of positive and negative charges? You create an electric field. This field, born from those uncovered ions, points from the positive side to the negative side. And it starts to act like a barrier, an opposing force that pushes back against the very diffusion that created it in the first place. So now we've got a real conflict brewing. That initial rush to spread out created a barrier. And now that barrier is going to start its own fight, creating a second competing current. So remember how we talked about majority and minority carriers? Well, even though the N side has tons of electrons, it still has a few stray holes. And the P side has a few stray electrons. This new electric field is perfectly set up to grab these minority carriers and just sweep them across the junction. This movement, driven by the field itself, is called drift. And as you can see, this drift current flows in the exact opposite direction of the diffusion current. This slide just perfectly shows the battle as it happens. At first, the diffusion current is massive and the drift current is tiny. But as more carriers diffuse across, that depletion region gets wider, which makes the electric field stronger, and that in turn makes the drift current grow. It's pushing back harder and harder and harder until, finally, a perfect, stable balance is achieved. The two opposing forces have fought each other to a complete standstill. Now, the really important thing to get here is that this is a dynamic equilibrium. It's not like everything just freezes. Oh no, electrons and holes are still diffusing one way, and minority carriers are still drifting the other way. But the two currents are now exactly equal in size and going in opposite directions. So the net result? Zero current flows across the junction. The system is perfectly, beautifully balanced. And this image is a fantastic way to picture the result. This whole balance is held in check by something called the barrier potential. You can just think of it as an energy hill. For another electron on the inside to make that journey across, it now has to have enough energy to climb this hill. And you know what? Most of them just don't, which is what stops the diffusion from just going on forever. And this is where it all comes together. Check this out. The top diagram shows the physical reality, those immobile positive ions on the left, negative on the right. The middle graph just plots that as charge density. But then if you do a little bit of math on that, you get the bottom graph, the potential. The shape and the height of that energy hill we were just talking about, they are directly created by the width and charge of the depletion region. It's all just different ways of looking at the exact same thing. Okay, wow, we've covered a ton of ground in this tiny, tiny world. So let's do a quick recap just to lock in all these key forces that define the p-n junction when it's just sitting there, doing nothing. Here it is, the whole story on one slide. First, you have diffusion, which is just majority carriers trying to spread out. This creates the depletion region, that zone of locked ions with no free carriers. That region then creates two things: the drift current, which sweeps minority carriers the other way, and the barrier potential, that energy hill that stops diffusion and holds everything in a perfect balance, where those two currents cancel each other out. So we've established the baseline. We now understand this delicate, dynamic equilibrium. This is the junction at rest. But, the whole point of electronics isn't to leave things at rest. It's to control the flow of current. So the big question, the really exciting question we're left with is, what happens when we intentionally disrupt this perfect balance by applying an external voltage? Because that, my friends, is where the magic really begins.